So, you know, I chose Sacramento for the state of California, but that was kind of arbitrary. I could have chosen Fresno or even San Diego or some other place, right? So the question is, how do we, does it matter what point we pick, or could we just pick any point as long as we make our radius big enough? What do you guys think? Should we just choose any old point of the set to go with?
Well, it would have to work for all x and y, so it wouldn't matter which one we pick.
Okay, so let's just try and pick it arbitrary. So just choose x naught, an element of A. This, of course, requires that A be non-empty. Otherwise, you can't choose a point. If A was empty, then, of course, it would be contained in anything. And it would definitely be bounded as well, because there would be no points to compare. So we may as well assume, so this is trivially true if A is empty. So we can just assume that A is not empty for the rest of the proof now, and so I can pick a point in the set. So it's just worth making that. That's like a technical comment that I probably wouldn't normally care that much about, but since I'm trying to be careful here, I would probably say that. Okay, so we've got our point, you know, here's the x naught. Now, how big of a radius do you think we should take? So we are assuming that A is bounded, so there exists an alpha. So we do have this number alpha on our hands. So let's claim that A is contained in a neighborhood around x naught of radius alpha. This would prove it, right? If we can get this to work, then we're going to be good to go. A is contained in some neighborhood. We're saying we can just choose any point, x naught, doesn't matter, and the radius is going to be that. Let's just check it. Let's check that this is true. So let's let, I don't know, we'll call it y be an element of capital A, right? I need to show that the distance, I need to show that y lives here. But that just means the distance from y to x naught would need to be less than alpha. Well, is it?
Exactly, about the same thing.
By the definition, it's definitely true, right? There exists an alpha greater than 0 such that for any 2 points of A, the distance between them is less than alpha. So look at that. You've got 2 points of A, so their distance has to be less than alpha. So there you go. We get y is in the neighborhood of x naught of radius alpha as needed. Okay, that's really simple. Really easy. To put A inside of a neighborhood, you just pick any point whatsoever, and you make your radius equal to the alpha that is given to you in the definition of bounded here. Okay, great. Let's go backwards proof. Let's assume that A is contained in some neighborhood. So let's assume that A is a subset of a neighborhood. So if there's a neighborhood, then usually we would write this as a neighborhood around some point with some radius. So let's just say where x naught is in x and p is greater than 0. Something like that. Okay, and we're going to try to show that A is bounded. To show that A is bounded, I have to come up with an alpha that's greater than 0 so that any 2 points are less than alpha apart. Does anybody have an idea? Alex?
If you make alpha be 2p.
Okay, so let's take alpha equal to 2p. Now, the reason for that, you might be already thinking about why is that true. Well, if I make my neighborhood here of radius p, what's the farthest apart that any 2 points could be? It'd be like, you know, this is my picture to show it's like 2p all the way across, right? So hopefully that kind of makes sense. So yeah, so I'm going to take alpha equal to 2p. Obviously, that's greater than 0. And we just have to claim that the distance between any 2 points is less than alpha. So then for x and y in capital A, let's just check that the distance between x and y is less than 2p. So does anybody have a suggestion? How am I going to show that the distance between x and y is less than 2p? inequality. Right, I need to insert another point in here. What point do you suppose I'm going to insert? What's the only other point that we see in the proof so far?
A 0.
X naught.
The x naught, exactly. So by the triangle inequality, we can write this like the following, right? We can actually put the x naught in the middle there, and the distance between, how far apart is x from x naught? Well, I don't know, but I do know that x is in A, and A is in here. So the distance between x and x naught is definitely less than p, and same thing for the other one, right? So this just gives you 2p, and you're good to go. Done with the proof at that point. Does that make sense, guys? Nice little problem. Nothing too hard about it. Okay. Okay, I think that's mostly the problems I was going to do having to do with metric spaces. I think I'll go on to another one. Is everybody okay if I go on? Okay, these are, this would be okay for a test, right? Not that bad. Pretty reasonable. Okay. So, I can always make up a definition and then go from there. In fact, let me make up another definition. Okay, so let's do number 3. Let's make another. I'm going to make another definition here. This one is going to be more for arbitrary topological space, and it's also going to be a nice preview for you guys. You're going to know it before everybody else in the class does, because we are going to need this concept later. So here is a definition to get this problem started. So let x comma tau be a topological space a point B in X is a limit point of some subset, I'll call it A, inside of X, if every open set U containing B intersects A minus the set B. So this is, again, a definition that I'm going to use to do this proof. Let's see if we understand it. So here's capital X again, and then we have our subset A somewhere here, right? So a limit point is going to be a point that's like either kind of inside of A or right on the edge of A. And even if you might even have a dotted boundary, and that's okay. So you could have a picture like this. So the idea is that if you make any open set around B, no matter where the B is, for B to be a limit point, every little open set that you could draw around B will actually intersect part of A. Oops. It intersects with A, right? Now, if A, let's suppose that A also has this point over here all by itself. That has some, what we call, isolated point. Well, if you draw a neighborhood around that particular element of capital A, right, that is not going to, this little a, if it's isolated, is not going to be a limit point, because here's an open set that is around that point, and it doesn't intersect the complement of that point, right? Because I have to take out the point itself. If I didn't take out this B, then this would be like a bad definition, because then, of course, every open set that contains B does intersect A if B is in A. And that would be, so everything inside of A would always be a limit point. What we're saying now is you can actually have elements of the set that are not even considered limit points of that set. In fact, if you take the integers inside of the real numbers. So if you just take this example, right? This set capital A has no limit points at all, because any real number that you try to pick, right, and you draw a neighborhood around that point, whether it includes an integer or not, right? It's sorry, I should draw a neighborhood that doesn't include any integer in it. So the original one I drew was better, right? But even if I pick this point, yeah, it's true that every open set containing 0 does contain a point of the integers. But remember, if I throw this particular point away, then there are no other integers in there. Just to be real clear what I'm talking about, when I say every open set intersects A minus B, I just mean that U intersected with the complement of B relative to A is not empty. There is something in every one of those intersections. So every time you take an open set, right, that has B in it, that open set will also have other points of A in it besides B. Make sense?
Mhm.
We're going to need to know this soon anyway, so we may as well learn it now. You guys will have a head start. Okay, so here's what I would like us to prove now. Prove that A is closed if and only if, so it's a closed set, if and only if A contains all of its limit points. So for example, Z is closed in R if you use the regular topology, the regular absolute value topology. We already knew that anyway, because if you take the complement of the integers, that's going to be an open set, and that's pretty easy to see. So, but now we're actually, we know that the integers have no limit points at all, if you believe what I just said. So of course, the integers contain all of their limit points, because there aren't any. There aren't any limit points to contain, so it's automatically true. This is automatically true for the integers. Therefore, the integers are closed. Okay, let's go ahead and try to prove this. You know, I don't know how, this is actually a fairly important concept. It may not always seem like everything you see is like super important all the time, but a lot of the reason I ask these questions is just for you guys to practice the proofs and like how to set up the forward and backwards arrows and how to write these things up, because this is something we need to still work on. I actually